Good morning, friends. Today we study the new topic column and strut. It is the subject of structural analysis 1. These are the content of our topic: introduction, classification of columns, slenderness ratio, types of beam and condition, assumption of Euler's formula, limitation of Euler's formula, and Rankine formula. First is the basic introduction about the column and strut. We know very well about the column. It is the vertical member of our structural component. Column are the member subjected to direct compressive force. A vertical member subjected to direct compressive force is called a column or pillar. Second one, strut. When the member of structure is any position and carrying an axial compressive load is called strut. Strut may be horizontal, inclined, or even vertical. A strut may also be an horizontal member. Load carrying capacity of compression member depend not only on its cross-sectional area but also on its length and the manner in which the end of the column are held. Equilibrium of column, there will be a 3 stage: stable, unstable, and natural. Critical, crippling, or buckling load. Load at which buckling start, it's called the buckling load. Column is said to have developed an elastic instability. Classification of column. Column will be classified according to nature of failure. There will be 3 types: short column, medium column, and long column. Short column, whose length is so related to its cross-section area that failure occurs mainly due to direct compressive stress only and the role of bending stress is negligible. Second one, medium column, whose length is so related to its cross-section area that failure occurs by the combination of direct compressive stress and bending stress. And last one is a long column, whose length is so related to its cross-section area that failure occurs mainly due to bending stress and the role of the direct compressive stress is negligible. Next topic is slenderness ratio. Slenderness ratio of a column is defined as the ratio of a column height to its least radius of gyration, where L is equal to equivalent length of the column, K is the least of radius of gyration, where K is equal to under root of I by A, where I is the least moment of inertia, A is equal to cross-section area. Load carrying capacity of a long column depends upon the slenderness ratio. For a good design, the slenderness ratio is as small as possible. Next topic is effective length of the column. The effective length of a given with the given and condition is the length of an equivalent column of the same material and semi cross sectional with hinge and having the value of a crippling load equal to that of a given column. Effective length of column mainly depend upon the end condition. So there will be a 4 type of the end condition in which slenderness ratio is depend. First condition, when the both ends are hinged, that time endless crippling pi square EI upon L square. Actual length will become a L is equal to L. When the both ends are fixed, that time P is equal to 4 pi square EI upon L square. That time equivalent length is equal to actual length divided by 2. Third one end fixed, other end free. That time P is equal to 2 pi square EI upon L square, that time equivalent length is equal to actual length divided by under root of 2. Fourth one end fixed, other end hinged. That time equation will be pi square EI upon 4L square and equivalent length is equal to 2L, where P is the Euler's crippling or buckling load, E is the Young modulus, I is the least moment of inertia, L is equal to equivalent length of column for given end condition. Column subjected to axial load, equal crippling or critical load, that time PCR is equal to pi square EI upon L square, where EI is your flexural rigidity and L is equal to effective length of the column. Assumption of Euler's formula. The column is initially perfectly straight. The cross section of the column is uniform throughout the length. The length of the column is very large when compared to its lateral dimension. The shortening of the column is neglected. The self-weight of the column is ignorable. The column fails due to buckling alone. The column material is a perfectly elastic, homogeneous, isotropic and obeys Hooke law. The pin joints are frictionless and fixed and are rigid. These are the some assumption of Euler's formula. We have to follow this assumption. There is a limitation of Euler's formula. Euler's formula is used for long column and neglect the straight due to direct compressive load. If a slenderness ratio is less than 80, the Euler's formula for mild steel column is not valid. In Euler's formula, that the critical or allowable stress and columns decrease with the increase in slenderness ratio. Long axially loaded column tends to defect about the axis of the least moment of inertia, the least radius of gyration, and it should be used for determination the slenderness ratio. Next one is Rankine formula. Euler's formula is applicable to the long column only, for which I by K ratio is larger than particular value. Also does not take into the account the direct compressive stress. Thus, the column of the medium length it does not provide accurate result. That time Rankine forwarded an empirical relation 1 upon P is equal to 1 upon P plus 1 upon P. So, P is the Rankine crippling load, PC it is your ultimate load, PE is your lyrical load, strut is equal to pi square EI upon L square, it is your Euler's formula. PC is equal to sigma U into A, it is a constant for material. 1 upon P is equal to 1 upon PC plus 1 upon PE. So 1 upon P is equal to PE plus PC upon PC into PE. That equation finally solidify P is equal to sigma C into A upon 1 plus A L by K square, where sigma C is your crushing stress and alpha is your Rankine constant. A factor of safety may be considered for the value of sigma C in the above formula. Rankine formula for column with other end condition P is equal to sigma C into A upon 1 plus alpha LE by K raised to square. Rankine formula can be used for both short and long column. The following value are for column both the below values of the column both ends: material, crushing stress and Rankine constant. Buckling loads. The load at which the column just buckle, it's called buckling or critical load or crippling load, and the column is said to have developed an elastic instability. The value of buckling load is low for long column and relatively high for short column. Factor of safety. Factor of safety is equal to crippling load divided by safe load. Column subjected to axial load or EULER'S crippling load is equal to pi square EI upon L square. EI is the fracture rigidity, L is the effective length of the column. EULER'S formula is only for long column, L by K is greater than 80. Now we study the example of column and strut. This gives the basic idea about how to identify the crippling load. Example number 1. A mild steel column 5 meter long and 50 mm diameter, which is fixed at one end, free at other end. Determine the EULER'S crippling load. Take the E is equal to 2 into 10 raised to 5 Newton per mm square. So this example gives some basic dimension or criteria. First, a mild steel column 5 meter long, so it gives the length, it's a 5 meter. 50 mm diameter, so it is the circular section. Then fixed at one end and free at other end, so it gives the end condition. So we have to identify the EULER'S crippling load. EULER'S crippling load, we know the equation pi square EI upon L square. This condition for both end hinged. So both end hinged, equivalent length is equal to actual length. But one end fixed and other end free, that time equivalent length is equal to 2 into actual length. So P is equal to pi square EI upon L square. So put in equation, P is equal to 3.145 2 into 10 raised to 5 EI upon 4 into L square. But for I of circular section, so circular section for moment of inertia, pi multiplied with d raised to 4 upon 64. Then after putting the value, we identified the I and put in equation. So finally we got the P 6052.2 Newton. Second example. A hollow long tube of 5 meter long with external diameter 40 mm and internal diameter 25 was to extend 6 mm under tensile load of 60 kN. Find the buckling load for the tube when used as a strut in a both end pin. Also find the safe load, taking the factor of safety as a 4. So solution give, first of all we write up some given data. First give the length, it is 5 meter. Both end pin or hinge, that time equivalent length is equal to actual length. So 5 meter is equal to 5000 mm. External diameter it is your 40, internal dia it is your 25. So it is hollow circular section. So moment of inertia about hollow circular section, we have the equation pi by 64 multiply with the external diameter raised to 4 minus internal diameter raised to 4. After calculating the value, we go to identify the area. So for the hollow section area, pi by 4 external diameter raised to square minus internal diameter raised to square. After the finding the area, we go to find the stress. We know the equation about stress, force divided by cross section area. We have the force, it is our 60 kN. Then after strain, so it is change in length divided by L. So and then after we can identify the E. So stress divided by strain. So we got the E. Now we using the EULER'S formula pi square EI upon L square. We have the all the values. So we can identify the P. Then after we have to identify the safe load. So safe load have the equation crippling load divided by factor of safety. We have the factor of safety 4. So we can identify the safe load. Okay. Next. Example number 3. These three examples give you different idea about to identify the crippling loads, EULER'S loads and safe load. Last one. The cross section of mild steel column is a hollow rectangular section with a dimension of 300 by 200 mm and the vertical thickness 25 mm. The length of column is 3 meter. Both ends are hinged. Frame the safe load it can carry using the Rankine formula. Take the factor of safety is equal to 3. Fc is equal to 300 Newton per mm square. Alpha is equal to 1 divided by 1500. First, we have to identify the moment of inertia. For moment of inertia, it is the hollow section. So 1 by 12 BD raised to 3 minus small bd raised to 3. So it is external and minus internal. Then after we identified the K, then after cross section area, then phi, we have the equation of for Rankine, factor of safety 3, so we can identify the safe load. This all the equation give the basic idea about how to identify the columns and strut for the different loading condition. Okay friends, we enjoy the PPT. Thank you.